Alright, it's Mr. Laidan again. We are going to proceed with the concept of isotonicity. Adjusting solutions by using different ideas. And today we shall be looking on determining isotonicity by using the molar concentration method. The molar concentration method. So to understand this, you need to know the concept of the dissociation factor or the dissociation constant. And because when we talk of the molar concentration, it's all about molarity. Now, molarity refers to what? Molarity simply refers to the number of moles dissolved in 1 liter of a solution. Number of moles of solute dissolved in 1 liter of a solution. Now, if we have something about the solution, that is to say we have something to do with dissociation. We have something to do with dissociation. In whichever dissociation, we need to have the dissociation factor, which is abbreviated as I. This is called the dissociation factor. So the dissociation factor is in correlation with the molar concentration method. So the dissociation factor can be calculated by the number, by checking the ratio between the number of particles which remained after dissociation, or the number of particles after dissociation, to the number of particles before dissociation. So to get the dissociation factor, which is I, we need to have the number of particles after dissociation divided to the number of particles before dissociation. So this gives the ratio of the number of particles after dissociation to the ratio of number of particles before dissociation. Let's consider this example. Example 1, what is the dissociation factor of sodium chloride having 80% dissociation in water? Okay, what is the dissociation factor of sodium chloride? So we need the dissociation factor of sodium chloride having 80% of particles dissociated in water. So dissociation, it means there is a separation of particles. So if we separate sodium chloride, that is to say this electrolyte after dissociation, it's separated into sodium particles plus chlorine particles, and that is 1, 1. Okay, so if 80% of the particles dissociated, that means before the reaction at 0 time there were 100 particles, 100% of the all particles. This is before, and after 8% of these particles dissociated, and this 80 signifies 8 for both sodium and chloride. And we need to know the total particles which did not dissociate after reaction. So if initially there were 100 particles and after 80 dissociated, that is to say 100 minus 80, we get 20 particles which did not dissociate. So to know the total number of particles after reaction, you need to get the sum of particles dissociated plus particles which did not dissociate, because both of them are found after reaction. So we add 80 of sodium and 8 of chlorine plus 20 which did not dissociate, because all of these are found after reaction. This makes a total of 180 particles. So the dissociation factor, total particles after reaction, 180 divided by particles before reaction, we get 1.8, and that is the dissociation factor. Let's check another example, then we move to the other concept. Let's check another example, then we move to the other concept quickly. Then example 3 says, what is the dissociation factor of zinc chloride having 80% dissociation in water? Now we are looking for dissociation factor of zinc chloride having what? having 80% dissociated in H2O. Okay, if we dissociate this zinc chloride, this comes into zinc, 2 will jump over there plus chlorine. Then after reaction, if we burn the reaction, that is 1 and that is 2. So if 80% dissociated, this means initially we had 100 particles, then 80 particles dissociated, that is 1 times 80. Then here we have 2 times 80 particles dissociated. Then the particles which did not dissociate means 100 minus 80, we get 20 particles which did not dissociate. So total particles after reaction, we have 80 plus 160 plus 20. This is 180, making a total of 260 particles after reaction. So the dissociation factor is the total number, the ratio of total number of particles after reaction divided by the total number of particles before reaction. This gives us 2.6, and that is the dissociation factor. Okay, let's move to the other concept. So how to calculate the sodium chloride equivalent? Previously, we were obtaining the sodium chloride equivalent from the table of sodium chloride equivalents of common drug substances calculated at 1% weight in volume. Now, what if we are required to calculate by ourselves the amount of sodium chloride? This is a method. Amount of sodium chloride equivalent can be calculated by using the constant of 17 L-iso. This is the molar freezing point constant. That is what is regarded as L-iso. Molar freezing constant of a drug times constant 17 after derivation. Then you divide by molecular weight of a drug substance. So in your question, you need to have the molar freezing point of a drug and the molecular weight of the drug. Then its ratio multiplied by 17 gives you the sodium chloride equivalent. Okay, then we have another formula here to check the amount of substance or the amount of sodium chloride, W, amount of sodium chloride. So the amount of sodium chloride in this sense is not as the amount of sodium chloride which we were calculating in the freezing point liberation. In this sense, the amount of sodium chloride W is given by 0.9 minus drug percent times the sodium chloride. Okay, the sodium chloride equivalent. So this amount will come automatically in grams in this formula. W is equal to 0.9 minus drug percent, meaning drug concentration, times its sodium chloride equivalent. So for instance, in example 1, calculate the sodium chloride equivalent of a drug. If its molecular weight is 187 and its molar freezing point is 3.4. So if you need to calculate the amount of sodium chloride equivalent here, use this proportion. This is 17 times L-iso of a drug, which is 3.4 over 187, which is its molecular weight. Then the sodium chloride equivalent will be equivalent to 0.31 gram. That is simple. So in case you have part 2 of this question, that how much sodium chloride is needed to make a 2% of this drug isotonic? Yes, let's say we have the concentration of the drug here. If the concentration of the drug was 2%, so to determine the amount of sodium chloride, you may use this proportion. Amount of sodium chloride is equivalent to 0.9, the concentration of sodium chloride equivalent to body fluids, minus drug percent, which is the concentration 2% times the sodium chloride equivalent, which we have calculated here. This is 0.31. If you multiply, what happens? This is 2 times 0.31 0.9 minus answer. Yeah, this is 0.28. You get 0.28. So 0.28 is the amount of sodium to be used. So in this sense, 2% weight in volume means that 2 grams are in 100 mils. So measure 100 mils of water, then add 2 grams of a drug substance, then add 0.28 grams of sodium chloride, then stir well, and the drug is already isotonic. Okay, let's check another example. We shall have the last 3 examples on this session. So in example 2, if you are calculating the amount of sodium chloride needed to adjust 1.5% atropine sulfate, what do you do here? We need the amount of sodium chloride, but the sodium chloride equivalent is, this is 0.12 gram, and the drug percent is 1.5%. How do you do? Use the last formula. W is equivalent to 0.9 minus drug percent times sodium chloride equivalent. So how do you do this? This is 0.9 times drug percent, which is 1.5% times its equivalent, 0.12 gram. Then W, the actual amount of sodium chloride, is 0.72 grams. Okay, so practically, if the question is like this, what do you do? The percentage of the drug was 1.5% weight in volume. This means that 1.5 grams were in 100 mils. So measure 100 mils of water, then weigh 1.5 grams of a drug mentioned, then weigh 0.72 amount of sodium chloride, dissolve the two in 100 mils and stir well, then the preparation is already isotonic. Okay, let's go back to the concept of molarity, because we are determining isotonicity by using molecular concentration method. As I said, molarity is equal to number of moles per liter. Number of moles of a solute divided in 1 liter of solution. So, but number of moles, remember, are equivalent to mass over molar mass or molecular weight. So if you substitute into the formula, molarity will be equivalent to mass over molar mass divided by liter, then that is multiplication after that. Okay, now we have this question here. This question says that calculate the molecular weight of compound X. So we need the molecular weight of compound X, which contains 9.06 grams. So the mass or weight, that is 9.06 grams. Isotonic solution, given the dissociation factor, is 1.8. According to this question, we are required to calculate the molecular weight. We have the mass and we have the dissociation factor. How are you going to do this? This is very simple. There is this equation here. There is this equation here, which says that the constant freezing point of body fluid is equivalent to 1.86 Ni. So this is the freezing point constant of body fluids, and this is the dissociation factor, their body fluids, and this is the number of moles times the dissociation factor. So what do we need here? We need the molecular weight. Mind you, molecular weight can be found from this formula. Number of moles is equivalent to mass over molecular mass. Okay, and if we are looking for the molecular weight, then if we make the subject molecular weight equals to mass over number of moles. Okay, so we have the mass here, but we have no number of moles. So number of moles can be obtained from here. Make number of moles the subject, that is freezing point over 1.86 I. Oh, okay. So N, freezing point, constant of body fluids, that is 0.52. You need to claim that and understand it all night. Then 1.86 times the freezing point, 1.8, you'll get N. Okay. 1.86 times 1.8. You get 0.1553. Then take mass here, 9.06 grams, divided by 0.553. Then you get 58.33 gram per mole. So at least this molecular weight can tell you something. 58.33 gram per mole. We may know that this substance was sodium chloride because this is the molecular weight of sodium chloride. Let us look at the last example. There is this simple formula here. In fact, this concept is in correlation with White-Vincent method. The White-Vincent method is all about adding water to make the solution isotonic. Then step number 2, adding an isotonic substance to make the required volume. So that is summarized in the following formula after derivation, that V, the required volume, is equivalent to 111.1 times the weight of a drug substance multiplied by its sodium chloride equivalent. This is a simple proportion we can use to determine the amount of water to add to a drug in White-Vincent method, then add the isotonic vehicle to make it isotonic. So in example 2, we are required to add the volume of water and then complete with the isotonic vehicle in the following ingredients. We have phenacane hydrochloride, phenacane, which has 0.06 grams, and sodium chloride equivalent of 0.16. This is sodium chloride equivalent. Then the next ingredient is boric acid with 0.3 gram with sodium equivalent of 0.5. Then we need to add water. Add the water, H2O, up to 100 mils. What do we do then? So the drug substance, we have more than one drug substance here. We have phenacane and boric acid. So find V1, then find V2 for boric acid, then add the 2. Okay, so V total shall be equal to V1 plus V2. Then we get the final volume. So let's try to do it. V1 is equal to 111.1 times weight, that is 0.06 grams of phenacane, times its equivalent 0.16. Then V2, 1111 plus 1 times weight of boric acid, 0.3, times its equivalent, 0.5. After you have got this, sum the answer, and that will be the volume. So the final answer will be 17.7 mils of water. So after weighing 0.06 grams of phenacane and 0.3 grams of boric acid are going to be dissolved in 17.7 mils of water. But this is not 100, which is the required volume. Thereafter, according to White-Vincent, add a sterile substance or the sterile isotonic substance like sodium chloride to make up the final volume. So that is all about the molecular concentration method. Let's meet in the next time.